The K series of computing and compensating gun sights were used by U.S. Air Force heavy bombers throughout World War II. They were intended to solve aerial gunnery's greatest challenge, calculating the deflection needed to hit a target from any position. In simple terms, deflection is how much the gunner needs to lead his target. Putting the crosshairs on the target and firing only works if the target is flying straight and level, and you are right behind him, also straight and level, and at point blank range. In any other condition, some amount of deflection is needed, and if it is not the precise amount, your bullets will miss. For a fighter pilot, this is difficult to solve during a dogfight, but at least he has the advantage of flying his gun. That is, his guns are always pointed in the direction of flight. But for a gunner in a turret on a heavy bomber, it is far more difficult as his guns can be pointed at any angle relative to direction of flight and in two different axes. The only way to make the turrets effective would be to calculate the full deflection solution dynamically for the gunner. This required something new, a computer, and a computing machine is exactly what the engineers at Sperry built with the K3 gun sight. Compared to other gun sights, this 30-pound sight was massive, but at a time when other computers were room-sized devices, a real-time computer that could fit in a turret was quite an achievement in mechanical engineering. The K3 computing sight was used exclusively in the Sperry top turret of the B-17. It connected to the turret with drive cables that provided the elevation and azimuth changes to the sight. The gunner only needed to input the wingspan of the target fighter. Why does the wingspan matter to the deflection calculation? Well, it doesn't, but when it is known, the gunner can use the sight to determine the range to target, and range plays a big part in the calculation. To determine the range, the gunner sets the target wingspan, tracks the target in the sight by moving the turret, and then centers the target in the reticle. He adjusts the range setting until the reticle frames the target wingtips, and now the correct range is established and the gunnery solution is ready. The way the sight calculates the solution is purely mechanical, with no electronics beyond a DC motor. An elaborate arrangement of gears, cams, and followers do the math and slew the sight head in azimuth to the projected deflection. There was also a corresponding computing sight for the Sperry ball turret, as used on the B-17 and B-24, and this gun sight was the K4. It was simply an inverted version of the K3 with some minor changes. For turret installations that were not designed for the bulky gun sight, such as the Martin top turret used on the B-24, a disassociated version of the K3 was made. This was the K9. The K9 is essentially a K3 in two parts, with the bulky computer unit mounted in the bottom of the turret, feeding the smaller sight head in the top of the turret via drive cables. The reticle of the K3 and K4 is illuminated with a unique GE Mazda 838 bulb with an integrated mounting plate. The K9 uses the standard GE Mazda 844. If the bulb failed, a backup ring and bead sight was available. The K3 and K4 provided a removable solid green sun filter glass, and the later versions of both, along with the K9, had a Polaroid variable density sun filter. There is another class of computing sights that are much simpler, the compensating gun sights. To understand these, we need to first break the full deflection calculation into two components, the ballistics and the target projection. The first component, ballistics, describes what happens to bullets fired at a given airspeed and altitude at a given angle relative to the direction of flight. The second component, target projection, describes where a target moving at a given speed in a given direction will be when the bullets would reach that point. While computing gun sights like the K3 solve both of these, the compensating gun sights only solve the ballistic component. Compensating sights were built for specific gunnery positions in the bomber, as the sight for the nose gun would have different ballistics than the sight for the tail gun. The gunner enters the airspeed and altitude, and flexible drive cables from the turret or gun mount pass the gun elevation and azimuth from center. Based on these inputs, the sight moved the reticle in elevation and azimuth to compensate out the ballistics. However, this is not a complete deflection calculation. You'll notice that range is not entered, and the reticle does not adjust on wingspan and range, but rather is a fixed two-ring reticle, as the gunner still needed to lead the target using the position firing method being used by all the other gunners, except the top and bottom turrets with their full computer gun sights. The K-10 compensating gun sight was designed for use in a tail turret, and the externally identical K-11 was used in the nose turret. Later in the war, the K-13 was introduced for the waist gunners, and it took directional input from the K-7 gun mount used at those stations. All three compensating sights used a two-ring, non-adjustable reticle, which was illuminated with a standard Mazda 844 bulb in the K10 and 11, although the K13 used an 836 bulb, which was not interchangeable with the 844. They all provided a Polaroid variable density sun filter and had backup ring and bead sights. One last gun sight to mention is the Fairchild K8 sight, used on Martin top turrets such as on the B-24. It is labeled as a compensating sight in its manual, but it appears to actually be a computing sight. It was used on the top turret, which of course is capable of firing in any direction, and it does require a range component. Like on the K3, the gunner inputs the target wingspan in the control box and uses a foot pedal to adjust the range until the reticle ring sizes up or down to frame the target. The sight then provides a full deflection solution factoring in target movement. So in operation and effect, the K8 is clearly a computing sight. Why it is called a compensating sight is unclear. Perhaps it is a case of semantics, or maybe there is an unknown technical distinction. Perhaps it had something to do with Sperry's patent on computing sights. Computing and compensating gun sights are examples of science and industry trying to solve the most complicated problems of war. While these sights were large, complex, and expensive, they did provide the bomber crew the capability to lay down accurate defensive fire in any direction. And it is largely these sights that made the U.S. heavy bombers the much vaunted flying fortresses in the sky. Some of the resources referenced in this video can be seen here. Thank you for watching. If you'd like to see a gallery of all of my gun sights of this type, please stick around, and feel free to contact me with questions.